Hello everybody, in this video we will discuss SN1 reaction of alcohol with HBr. Let's figure out why this is called SN1. Okay, so S stands for substitutions. So you are substituting a group. So in our problem, if you notice, we are substituting a group OH with something else. And what is that something else? That something else is N. So this means Br, which is in this case, actually it's going to be Br minus. So you are substituting a OH with Br minus, which is our nucleophile. So N stands for nucleophile. So we are substituting a group with a nucleophile. That's why it's called SN. And what 1 represent? 1 represent unimolecular reactions. So what is a unimolecular reactions? A unimolecular reactions is when one molecule is involved in the rate determining step. So for example, let's say you have a molecule called AB and it's split it into two, A plus B. And this is a rate determining step. So let's say the rate of the reaction depends on AB. So if you have a multi-step reactions and the rate determining step, in the rate determining step, if only one molecule is involved in to determine the rate, or in this case, one molecule split it into two, then that's a unimolecular reactions. What would be a bimolecular reactions? In bimolecular reactions, if you have two molecules, the rate of the reaction depends on the two molecules to make something else. Okay, so in this case, you have two molecules that's going to depend, and that's why it's going to be a bimolecular reactions. Okay, so let's delete this and we'll continue our problems. All right, so let's delete this. Okay, so how the mechanism progress. So I have drawn out every single carbon atom for a reason, so that you have a better visualizations. So let's look at the mechanisms. So you have carbon. So what type of alcohol this is? So this is, we call it tertiary alcohol. So here is why. So the way you figure out this is tertiary alcohol is you look at the OH group connected to the carbon atom. So in this case, OH group is connected to the carbon atom here. So this, the carbon atom that is connected. And then look at how many other carbon atom it is connected to. It is connected to 3 other carbon atoms, right? So when it's connected to 3 other carbon atoms, that's going to be a tertiary alcohol. So SN1 reactions is predominantly happens with tertiary alcohols. All right. So if the carbon atom is connected to 2 other carbon atom, that would be your secondary alcohols. So you will see more problems in the future videos. So let's look at what exactly is happening. So we know that oxygen has lone pairs. How many? 2 lone pairs. So what it will do is it will attract a proton, specifically acidic proton. And where is that acidic proton is? The acidic proton will be provided by HBr. So this would attract the acidic proton. And what would happen to these 2 electrons? These 2 electrons go towards bromine. So if you know, bromine has already 6 electron or 3 lone pairs. Now it's going to bring both of these 2 electrons back towards itself. So let's draw it out. What would happen? So we will get CH3, CH3. Nothing changes here. We got O. And then it has already a hydrogens. Now it will connect another hydrogens from the bromine. The other lone pair will stay as it is. I'll get back to this molecule in a second, but let's look at bromine. So we got bromine had 6 before. Now it has collected 2 more. And bromine has 8 electron and extra electron, so it will have a negative charge. Let's look at here. So now oxygen has 3 bonds. And it forms 3 bonds by giving away 1 extra electron. So as a result, it will have a positive charge. So here's the shortcuts that you want to remember. When oxygen has 2 bonds, it is neutral. When oxygen has 1 bond, it is negatively charged. OH, the charge on oxygen would be negative. When oxygen has 3 bonds, H, 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 it will be positive. So this trick you can use for rest of your organic chemistry. So just look at how many bonds it is making. If oxygen is making no bond, then it will be 2 negative. Okay, so this is the trick you can use for futures. Okay, maybe we should remove these to make some space for us. All right, so let's delete this. Okay, so let's go back to our mechanism. So you notice here we have a positive charge on oxygen because it's making 3 bonds. Now, what can happen here? Every single time you make a positive charge on an oxygen, you want to neutralize it. And the way you can neutralize it is by removing a bond. So one thing I can do this is if I get rid of my proton, let's say I'm getting rid of this proton here. So this H is going away. So let's say the H is going away. And what would happen to the electron here? This electron would be part of oxygen. And how many bonds oxygen is making? It's making 2 bonds. So oxygen will become neutral. So let's not do that. So let's say if we remove this one here, and this bond is gone, that means the positive charge will be gone. So how does this molecule looks like? This molecule is exactly same as this molecule. Okay, so as a result, if I lose that proton, I can also, so that means I'll be going backward. So that's why this reaction is in equilibrium. Okay, let's bring back our proton the way it was before. And let's bring back the proton. Let's bring back the charge. The charge here was positive. Okay. Every time you create a positive charge, you're going to neutralize it. One way neutralize is to remove the proton. That would essentially drive the reaction backward. But let's move forward. Let's break this bond here. Let's break this bond here. Let's break the bond right here. How many electrons we have in this bond? 2 electrons. So we can bring them back here. And what will happen is you will make this. Okay, so you notice now carbon atom has does not have octet. It has lost electrons. So it would be positive charge. And this is called carbocation. To be precise, what type of carbocation? When you have carbocation, look at the central carbon atom that has the positive charge, and then look at how many other carbon atoms it is connected to. It is connected to 3 other carbon atoms. So that would be your tertiary carbocation. Okay. And what happens to the group? What happens to the other group? So we created water. Water is our living group. So in this case, the group right here has gone away and oxygen has becomes neutral right now. So the water is our living group. So let's look at the mechanism here. This step is critical. So if you noticed, this molecule here split into 2 molecules, right? So the molecule here, it's split into 2 different molecules. So that's an example of dash reactions, unimolecular or bimolecular. Remember, Br minus is not participating. So this one molecule has split it into 2 other molecules. So this is our rate determining step of the reactions. So this is rate determining step. And in this step, the reaction is actually unimolecular. And this is why the whole reaction, we call it SN1 reactions, okay? All right, so now we have a carbocation. If you remember stability of carbocation, which one is the best? tertiary is the best, then secondary, then primary, and then the methyl carbocations. Okay, so tertiary is our best carbocations. So right now, the reason the water left, because by removing the water, you are creating a carbocation that is good enough to be stable. Uh, it will be neutralized as soon as it's being made, but it's good enough to be stable. So there are a couple of ways you can move forward from here. So once you create a carbocation, it will attract a nucleophile immediately. Now there are a couple of possibilities. Water could come and attack the nucleophile. If it does, that's basically going backward, wherever you started from. It can happen. Like, I'm not stopping it. It can happen. So if it does, it's basically going backward. But let's move forward, right? We're going to move forward with our life. So what would happen is, we know that there is a Br minus chilling in our reactions. Remember, don't forget the Br minus. We created the Br minus in our step before. So if the Br minus come and attack, that would make us this. And once you make the Br connected, it's very difficult to go backward, because water is not going to be a very good nucleophile to replace Br. All right, so that's pretty much, we got our product. So let's recap everything what we did here. This is your final product. So let's recap everything. I will do another complex problem in the next video. So why this is called substitution reactions? Well, we are substituting OH. Why this is called substitution nucleophilic? Because the nucleophile is Br minus. We are substituting with a nucleophile Br minus. Why this is called unimolecular? Because our rate determining step has one molecule as a reactant. Okay, and why we have one molecule? Well, because once the leaving group goes out, we are left with a carbocation, which is tertiary carbocation, which is decently stable enough. And once you create the carbocation, your Br minus will attack. All right, so let's do another problem. Before I will write down the question here, and you all do this problem on your own before I give you the answers. All right, so what is the product going to be from these reactions? And the answer will be in the next videos. Let's stop here.